So far we have been considering that one-dimensional case, and we didn't discuss where the propagation of waves was occurring. One particular case is the case of guided waves. Now, what is a guided wave? Well, we have a certain structure, maybe a parallel plate or maybe a coaxial cable, and we are propagating a wave inside that structure. We're going to use a harmonic dependence of the type e to the j omega t, and we are assuming that the guiding structure does not change along the z-axis. And we're going to have a wave propagating along this z-axis. Now, we don't know how the fields will be, but it can be shown that the field, the electric and the magnetic field, will respond to this sort of expression. We have a certain field distribution that will change along the x and y axis, and we have a wave propagating along the z-axis. And then the solution for the z-dependence is given by this, where gamma is the propagation constant, something that now we don't know its value. And the specific values of that field along the x and y coordinates will depend on the characteristics of the waveguide, its shape, the materials for which it's made, and so on. Now, if we're assuming that this is the type of solutions that we will have, and going back to Maxwell's equation, to Ampere's and Faraday's law, we can apply them, we can rearrange the terms, and well, it's a little bit lengthy, but we obtain something like this. Now, what is important here? Well, the important thing here is that we can see that here we have the x component and the y component of the magnetic field, and we will call these components the transversal components because they are perpendicular to the direction of propagation. They can be found if we know the z component of the electric field and the z component of the magnetic field. Now, the z components of the fields we will call them the longitudinal components, because are those components that are its direction is coincident with the direction of propagation. And notice that we have a similar situation for the electric field. The transversal components of the electric field can be found if we know the longitudinal components of the electric field. So this is the first thing. We only need to find a solution for the longitudinal components of the field, and from that we can find those transversal components. So here we have written what I just said before, and usually when we classify the solutions there are three different cases. If the z component of the electric field is 0, we will call that a TE wave, a transverse electric wave, because there is only components of the electric field in the transverse direction. If it's in the case we have the z component of the magnetic field 0, we will call this a TM wave, and if both Ez and Hz are 0, we will call that solution a TEM wave, or a transverse electric magnetic wave, because there are only transverse components of the electric and magnetic field. Now, if we are looking for a TEM solution, we are assuming that Ez and Hz has to be 0, and if we remember our relationship, if those two components are 0 and I want a solution different than the trivial solution, that is all the components being 0, this is only possible if gamma squared plus k squared are also 0, because in that case there can be a solution for the fields Ex, Hx, Hy, Ex and Ey different than 0. But notice, if we have to meet this condition, that means that the propagation constant that was an unknown is directly either plus or minus jk, and remember that k was directly omega, there is a mistake here, actually that should be k is omega square root of mu epsilon. So For a TM solution, the propagation constant depends only on epsilon and mu, but not on the shape of the waveguide. Propagation occurs at all frequencies, there is not any restriction, and it can be shown that for always in a guided wave, for the TM case, we have something that is, we have a certain relationship between the components of the magnetic field and the electric field, and that relationship is given by the impedance medium as we had seen in the one-dimensional case. Now, it's also straightforward to show that in that case the electric field and magnetic field are perpendicular, and if we compute the Poynting vector as we had defined it before, the Poynting vector is directed along the z-axis, which is where we have the propagation, and can be computed directly from knowing the transverse component of the electric field. Now, under what conditions we have a TM solution? Well, if we go back to the wave equation, which is this one, and we know that we have solutions of this type for the propagation in a guided structure, we can write this Laplacian operator, which is the second derivative along the x, y, and z axis. We can write it in this way. We're just giving a specific name to this, the derivative along the transversal coordinates. We can rewrite the wave equation in this way. That's a general case, but for a TM mode, we had just seen that gamma squared times k squared had to be 0. So if this is the case, for the TM mode, this is also true. Now, if this has to have a non-trivial solution, that is a solution for which the transverse fields are different than 0, that's the condition we have to meet in order to have a TM solution. But now, if you look at these equations, those are Poisson's equations for the electrostatic and magnetic fields for a source-free region. So now we can see the condition that we need to meet to have a TM solution. For a TM solution to exist, the transverse section of a guiding structure must have a non-trivial solution for the static fields. Now, maybe this is a very strange way to state it, but I think now you'll understand it. Imagine we have those three types of guiding structure: a coaxial cable, two wires, and a hollow waveguide. And we would like to know which one of these structures is able to support a TEM mode. Well, the only thing you have to do is do the following mental experiment. Connect in this coaxial cable, put a battery, and imagine if there is a solution for the DC field in this structure. And of course, we can imagine that if we apply a certain voltage into these two elements, there will be a certain solution for the static field. So that means that that structure is able to support a TM mode. Also, for the two wire, if I take those two wires and I put a battery here, I can imagine that there will be a certain solution for the electric field. And what happens with a hollow waveguide? Well, I can see that if I put a battery here, actually what I'm doing is short-circuiting, and the fields inside this hollow waveguide, the DC field inside this hollow waveguide, will be 0. So it doesn't have any other solution that being 0. It only has a trivial solution. That means that this hollow waveguide cannot support a TM mode. It has other solutions. It can propagate TM or TE modes, but not TEM mode.